Hello, welcome back to Algebra. We're going to cover the incredibly crucial topic called factoring the greatest common factor from a polynomial. This is part 1 of 2. We'll introduce the concept, we'll work some important problems here to get your skills built, and then we'll work some more complicated problems in the next lesson. So I want to define what factoring is for you, tell you why it's important, and then we're going to kind of go from there, right? The good news is it's very, very simple to understand. The bad news is factoring in algebra gives most students problems in the beginning. It's one of the very first things that you encounter in algebra that I can't even describe it without showing you a problem, but it just gives students, it makes life hard for students sometimes. Because up until now, we've solved equations, we've learned how to multiply things, we've learned how to add things. All of that's kind of cookie cutter. With factoring, you have to think a little bit more creatively sometimes. You have to kind of like try a few things and be willing to fail a little bit to get to the right answer. Now, I said fail is really the wrong word, but you have to be willing to try a few different approaches to get the right answer. So what is factoring? Factoring, you're going to get a definition in your book. That's fine. I'm going to show you my definition, which I think is a little easier to understand. Factoring is when you're trying to figure out what things will multiply together to give you whatever problem you have. Another way to think of it, a better and a simpler, easier way to think of it, is factoring is distribution in reverse, right? Let me say that again, distribution in reverse. Let me say that a third time. Factoring is distribution in reverse. So let it sink in. If you can remember that, it'll be very simple. Remember what distribution is. It's when you have a term in parentheses and you have something outside the parentheses. And then we take and multiply that thing inside and we distribute it to each of the terms inside the parentheses. That's what we call distribution. Now with factoring, we're going to take the answers that we got to all those problems and we're going to go backwards. And we're going to start with the answer and we're going to reconstruct the parentheses and the thing that sits out in front to go backwards from the answer to get to kind of reverse distribution. That's what we call factoring. All right, so let's give a couple of examples. I'm not going to write this definition of factoring down because it's not a really mathematical definition, but ultimately factoring is distribution in reverse, and that's what I want you to remember. So let's give an example really here. Let's take a term in algebra that might look like this, x plus 2. Now, you look at x plus 2. X is a variable and 2 is a number. They're completely different. X is like apples and 2 is like oranges. You can't add them together. You can't do any multiplication. I mean, everything is different between these two things because this can represent anything and this is just a fixed number. So because there's absolutely nothing in common between this and this, there's no commonality between these two things at all, you cannot factor it. You can't factor this expression. It's impossible to factor it. Why? Because there's no commonality. Ultimately, factoring is all going to be about looking at every little term and figuring out what is common to everything. What is common to everything? I'll say that a third time. What is common to every term? That's what we're going to be looking for. But because there's nothing common here, we can't do anything. So we just write it down. I wrote that down to show you that sometimes you can't factor things. But let's take a very simple change to this problem. Let's take 2x plus 2. Now, let me ask you something. Is there anything common between these terms? Well, the first thing you notice is there's an x here, but there's no x there. So x obviously is not common to either one of those terms. But obviously the big elephant here is that you have a 2, which is also in this term multiplied times x, and also by itself. Now, agree, they're not exactly the same because there's no x here. But the numbers are exactly the same. So what we want to do is we want to identify what is common to both of these things. And we want to, almost like we can reach into both of those terms and we want to yank it out and we want to figure out what is common to both of those things. Everything joined by a plus sign. We want to figure out what's common. In this case, it's 2. And we're going to reach in with some hands, grab the 2's, and we're going to literally pull them out. That's what we call it, pulling out the 2's, pulling out the factors. We'll talk about a little more about factors in a second, but 2 is a factor of both of those terms. Okay, that's why it's called factoring. We grab the 2's, we yank them out. So what happens when we do that is we take those 2's and we pull them out. But we can only grab 1 2 from here and 1 2 from here. So we pull them out as a common thing. And we have to open up a parentheses and we have to figure out what is left over here, such that when I take this 2 and I multiply it by whatever is left over, it gives me what I started with because they're equal. These have to be equal. So 2 times what will give me 2x? 2 times x will give me 2x. So I have to put an x here. And then I know that there's going to be a plus sign because there's a plus sign here. And then I know if I distribute this 2 times x, I'm going to get this 2x, but 2 times what here will give me the 2 here. 2 times what is 2? You all know that 2 times 1 is 2. So this is what we call the factored form of this. And now you can see very clearly why I told you the real definition of factoring that's easy to understand is its distribution in reverse. If I give you this problem and I say, simplify this expression, you know how to do that. We distribute the 2 into here, giving 2x, and then into here, giving 2 times 1 is 2, which is exactly this, 2x plus 2. But now we're going backwards. I'm giving you the answer, and I'm saying, what can you pull out that's common to both of those things, yank it out, and then figure out what must go in here to make them equal. So literally what you do is you figure out what we call the biggest factor here. So let me go and write a few things down, which kind of definitions here. So let me draw a little arrow here and a little arrow here and tell you that these things are called the greatest common factor. Now, almost everywhere you'll see this represented as GCF, greatest common factor, of each term. I'll go ahead and write that down as well. Of each term. Why is it called the greatest common factor? Think about what those words say. Greatest means the largest, right? Common means common to both of the things, right? And factor is what we said. Factor is something that's multiplied by something else to give you something. So 2 is the biggest thing that's common to both terms that, obviously because it's common to both terms, it's going to be multiplied by something to give me my original thing. That's the factor part of it. Factor means kind of like multiplicative term, right? But anyway, it's the biggest, in this case it's just a number, but it's the biggest number common to both terms. That's what it means, greatest common factor of each term. All right? And factors in general are numbers that are multiplied together to give us something. So we can just take that 2, pull it out, figure out what goes in the middle. This is what's called the factored form. So if you were on a test or something and the question was factor this expression, then you would just circle that. That's the final answer. The good news about factoring is that you always know if you're right, because all you have to do is take your answer and multiply it out again, and you should get what you started with. Otherwise, you've done something wrong. So you can see right away it's 2x plus 2. Boom, you got the right answer. Now let's just move through this. You're going to see quickly how easy this is once we do a lot more examples. What if we change it a little bit, 6x plus 3, right? So what we're going to do is we're going to look at each of these terms and we're going to figure out what is the largest common thing, the greatest common factor of both of these terms. Well, x is not even present in both of the terms, so x cannot be a common factor. So it has to do something with the numbers, but then you say, well, wait a minute, these numbers are different. 6 and 3 are different. They're not 6 and 3, neither one of them is common to both, right? Well, let's talk about it a little bit more and see. If I wanted to figure out what this term here, 6x, really is, what do I have to multiply together to give me 6x? Well, we say we're going to list the factors. The factors of 6 times x is 6 times x. Notice I drew this little tree here. This means that it's pointing up here to the 6x, so I'm going to write down here what multiplied together must give me this. And it's obvious because 6 times x gives me 6x. However, the factors here we can say are, let me take away the multiplication. The factors are 6 and x. However, 6 can also be split up into factors of its own, right? Because there are other things that can be multiplied together to give me 6, right? I'm talking about factors other than 6, and 6 times 1 is 6, okay? I'm talking about other factors, right? There's other things that can be multiplied together to give me 6. What about 2 times 3? That can also be multiplied to give me 6. So you see that when I really look at this first term, the factors that can be multiplied together to give me 6x really are everything at the bottom of this tree. 2 times 3, which gives me 6, times x. That is really what we call the factor tree, right? 2 times 3 times x will give me 6x, right? So these are the factors that matter here, right? Now for 3, the factors of 3, I'll just write it here, the factors, it's just going to be 1 and 3. 1 times 3, right? Gives me 3. I can't pick anything else that multiply together to give me 3. So remember what the big picture here is. I'm trying to figure out what is the largest thing common to this term and to this term. But you see, there's a 3 that's a factor here, and a 3 that's a factor here. So in fact, I am able, even though it doesn't look like there's anything common to these things, it's telling me that the biggest thing common to both of these things is actually the number 3. It's the greatest common factor, because 3 is present in both of these terms in terms of the factors that make up what is multiplied together to give me these terms. That's what a factor is. It's just whatever's multiplied together to give me this stuff. 3 is the biggest thing common to both of these things. Then I open up a parentheses and I have to figure out what goes on the inside. Then you do distribution in reverse. 3 times something will give me 6x. Well, 3 times 2 is 6, and the x has to be there to give me the 6x. The plus sign is here, so I have to join it with a plus sign. 3 times what gives me 3? It's going to give me 2x plus 1. And then you can always check your answer, because if I cover this up, 3 times 2x is 6x, 3 times 1 is 3. That's exactly what I started with. This is what we call the factored form of this. So we're starting with simple problems, but every problem of factoring will look like this. You just look at the terms, figure out what is the largest thing common to every one of those terms. It has to be common to all of them in order to pull it out. Once you pull it out, then you wrap your parentheses, or write your parentheses down and figure out what must be present in the middle to then make the multiplication correct, right? And it's hard to explain why this is useful now. I know you're looking at this like, well, why do I need to know this? Well, I'm telling you that when we get a little bit farther into factoring, we will be solving lots and lots of equations where you'll pretty much have to know how to factor in order to solve the equations. Up until now in algebra, we've solved lots of equations that didn't require factoring. But very, very soon we'll be solving what we call quadratic equations, and those require factoring in order to even solve them at all. So we have to get good at this, which the good news is very simple once you get the hang of it. Now let's move over to the other board and write a slightly more complicated problem. What if we have x squared plus x times y? And I say, I want you to factor this and tell me its factored form. Now, when students look at this, well, especially this, they can very easily see I pull out the 2, no problem. When they look at this, they can very easily see, okay, I can pull out a 3. That's kind of common to both. Okay, no problem, after I explain what factors are. But when students look at this, oftentimes they're like, oh my gosh, I have no idea how to do this because I don't understand. There's no numbers here other than the exponent. But all you have to do is look at this term, look at this term. What is common? Obviously, there is no y in this term at all, so it can't be a factor, right? If it helps you, you will get good at this without doing this down the road. But if it helps you in the beginning, just write the factors of each thing. What multiplied together can give me x squared? Well, it can only be x times x. That's the only things that can be multiplied together to give me x squared. So these are what we call the factors of x squared. Factors just means things that can be multiplied together to give me that. That's what that word means. And what are the factors of this thing? Well, x times y is pretty simple. It's just x times y. There's nothing else I can do simpler than that to write it down. And there are no numbers involved, so I don't have any of those. So the factors of this are just x times x. The factors of this are just x times y. So then I look and say, well, what is the largest thing I can pull out from both of these? Well, I can pull out a single x from here, and that would then allow me to pull out a single x from there. I cannot pull out an x squared from both of them because although there is an x squared present here, there is only one x in this thing. So remember, when you're figuring out what you can pull out as a factor, it has to be present in all terms of your expression. So even though I could pull out an x squared from here, I don't have an x squared here. So I can't pull it out as a factor because it isn't present as an x squared everywhere. Only one x can be pulled out as a greatest common factor because it has to be common to all terms. So I can only pull out a single x, and then I just realize now I've got my factor, and now I'm going to figure out what needs to go in the middle here to make it true. X times something will give me x squared. That something is x. There's a plus sign here, so I'll join it with a plus sign. X times something gives me xy. That has to be y. And then you double check yourself. X times x gives you x squared. X times y gives you xy. This is what we call the factored form of that expression. All right. Now, as we crank through some future problems, I'm going to take the training wheels off. I'm going to stop writing down the factors underneath everything, like I've written the factors down, because as we go forward, you will get very good at looking at terms and figuring out what the factors are without writing these trees down everywhere. But in the beginning, it is really helpful, so that's why I did it. But ultimately, if you get stuck, you can always go back and write down these little trees to help you figure it out. So let's increase the complexity slightly. What if I had 10x squared plus 5x squared y? And I want you to write the factored form of this. So what would be common as far as numbers to both of these expressions, right? Well, 5 times 1 is 5. 5 times 2 is 10. That's the biggest thing that I can actually pull out, because whatever you pull out has to then be multiplied by something to give you this, right? So I'm going to pull out a 5. It's the biggest thing common to both of these guys. And then I look at the variables. There's an x squared here, and there's also an x squared here. So I can also pull out an x squared. Here there's a y, but there's no y's at all here. So he's not a factor of both. Of course, the y is a factor of this term, but he's not a factor of all of that one, so that one at all, so I can't pull it out. So that is the largest, greatest common factor I have. And now I'm going to try to see what goes in the middle. 5x squared times something will give me 10x squared. Well, that something has to be 2. 5 times 2 is 10, and the x squared is there. Then I join it with a plus sign, and then I have 5x squared y. So 5x squared times something will give me this. The only thing that makes sense is the letter y. Then you check yourself. 5x squared times this gives me 10x squared. 5x squared times this gives me 5x squared y. And this is the final answer. Now, the other thing I want you to do and get in the habit of is, well, you could also write it as, I guess I should say, 5x squared. A lot of times we like to write the variable first, so you might see it written as y plus 2 in the middle there. It's the same exact thing. The other thing I want you to do is, after you factor something out, take a look at what's inside your parentheses, and just to make sure that there's nothing else common inside of there that you might have forgot or didn't notice at the beginning. Make sure that you can't factor it any further. And you see that you have a 2 and a y here, and there's nothing common, so you can't factor anything else out. Let me give you an example of what I'm talking about, why you want to do that. Let me do this problem again. Let me go here. Let me just say that I noticed that 5 was the greatest common factor. So let's say that I accidentally noticed that, or I correctly figured out that 5 was the greatest common factor of the numbers, but I completely forgot or didn't notice that the x squares here were common factors also. So if I do that, then 5 times what gives me this? It's going to give me 2x squared. That'll give me the 10x squared. And then over here, 5 times what gives me this? It'll be x squared y. So this is the answer, but then I'm about ready to circle it, and then as a double check at the very end, I go in here and I say, are there any other common factors to these terms? And I notice, oh, I missed it. There's an x squared here and there's an x squared here that I can pull out. So don't erase and start over. Just write another equal sign and say, well, the 5 is here, but then I notice I can pull this x squared out as well, right? And so then, if you cover up the 5, x squared times what will give me this? I need to have an x here. X squared times what will give me this? I need to have a y here, right? The 5 was coming down all along, but I just basically forgot to factor something else out here. So then you can see that this is exactly what we got from before. So when you finally factor something, always go into the parentheses and just make sure that you got everything, to make sure there wasn't anything remaining that you missed the first time that was common to both of them. All right, so let's take a look at the next one. What if we're going to increase the complexity a little bit, 3p cubed, 3p cubed times q plus 15 p squared. What is common to both of these as far as numbers? Greatest common factor. Well, you know that 3 times 5 is 15, so you know it's a factor of 15. And 3 is obviously here, so it's a factor of itself. So the largest factor that can be divided into, is another way to look at it, both numbers, is the number 3. So that's going to be the greatest common factor of the numbers. The p's, I have 3 p's here in p cubed, but I only have 2 here. So because it has to be common, I can only pull out 2 of these p's, right? And there's 1 q here and there's none there, so it cannot be a factor at all. So the thing I pull out must be present in both of them. Then I say, this times what gives me this? Well, I need 1 more p, and then I also need a q to give me this. Plus sign from here, and then this times what gives me this? I need a 5, obviously. And the p squared is already going to come along for the ride, so this is going to be the answer. So it'd be 3p squared times this plus 5, and you just double check yourself. This times this will give me 3p cubed times q, and this times this will give me 15p squared, and that'll be the final answer. And you can always double check yourself. Is there anything common to these terms in the inside? And there is not. There's a 1 here, there's a 5 here, there's no Q's or P's over here, so I can't pull anything else further out. All right, let's take a look and switch it up a little bit. And what if we have something like this, slightly larger numbers, 49 x cubed plus 35 x squared y. And I tell you, factor that. Now you have to kind of get good at looking at numbers and figuring out the factors of numbers right away. But whenever you kind of think about your multiplication tables, 49 and 35, immediately you should start thinking about your multiplication tables. What can be divided into both of those numbers? You know, the biggest whole number that can be divided into those numbers, that's going to be the biggest factor. And the number 7 should pop in your mind because 7 times 7 is 49 and 7 times 5 is 35. If you can think of a larger factor than that, then use it. But that's the biggest one I can think of off the top of my head right now, so I'm going to go with it. And if I get to the answer and I see that I can factor more out, then I'll do it at the end. But for now, I know that 7 is the biggest thing that I can pull out, so I'm going to go ahead and put a 7 here. That's for the numbers. Now I look at the variables. I have 3 x's here and 2 x's here. So I have to have commonality, so I can only pull out x squared. There's no y at all here, so I can't pull it out. Now this times what will give you this? Well, 7 times 7 is 49, so a 7 has to go in there. I need another x to give me x cubed, so I have to write an x in there. You should double check yourself that this multiplies to give me this. Then I have a plus sign here. 7 times 5 is 35. The x squared is taken care of from this, so I don't have to do anything there, but I do need a y because I need to have a y over here. Then you double check yourself. 7 times 7 is 49. X squared times x is x cubed. 7 times 5, 35. X squared will come from here and the y will come from here. So this multiplied out gives me this. And then I double check. 7 and 5, I can't think of any bigger factors that will divide into both, so I can't pull anything else out. X and y are completely different. So this is the final factor form of that expression. All right, just a couple more just to get a little more practice. Literally, I think we have 2 more here. They're going to get slightly larger. What if we have 25 x y squared times z plus 15 y squared z squared? First thing you do is look at the numbers. What is the largest number that you can think of that will divide into both of these? Those will be the biggest factors. Obviously 25 and 15, the biggest thing you can think of off the top of your head is 5. So put the 5 out there. Then you look at variables. I have an x here, but I don't have any x's here, so that can't be a factor of both. Y squared, that's common, so I can pull out a y squared. And then z and z squared, so that's good. I want to pull out a z, but I only have 1 here, and I have 2 here, so it has to be common. I can only actually pull out 1 of them. Then I open my parentheses, and I figure out this times something has to give me this. So 5 times 5 is 25. And then I need an x to give me this, so I need an x here. And then the y squared is covered here, and the z is covered here, so that's it for the first term. I join it with a plus sign, and then 5 times 3 is 15. And then I have y squared here, and then I have a z times, I need to put another z here to give me z squared. And then you double check yourself. 5 times 5 is 25. X, y squared, z, x, y squared, z, that's good. Then 5 times 3 is 15, and then I have a y squared, and then I have a z squared multiplying through. Let me just double check myself and make sure I got the correct answer. That is correct. 5y squared z, 5x plus 3z. That's correct. I didn't say it wasn't tedious. I just said that it's doable and it's easy to understand. But you do have to be very careful, and I do recommend that you put your fingers on your paper and just double check yourself. If you just do this and move on to the next problem, you will probably get some wrong answers. Last question. 24 r squared s plus 36 rs squared times t. I want to factor this. I want to look at commonality. I look at this and say, what can I divide into both? And the first thing I think of is 6, right? That's what I think of first, is 6. 6 times 4 is 24. 6 times 6 is 36. So I'm going to pull that out, 6. And then I look at variables. I have 2 r's here, but only 1 here, so I can only pull 1 out. I have an s here and an s squared here, so I only have 1 here, but 2 here, so I can only pull a single s out. And the t is present here, but it's not present at all over here, so I cannot pull it out at all. So I'm going to pull out 6rs. Now this times something has to give me this. 6 times 4 is 24. I need an r squared, so that means another r here needs to be written down. I need an s, that's going to come from the multiplication, so I'm good there. I'm going to join with a plus sign. And then 6 times something is going to give me 36. 6 times 6 is 36. I need a single r. I already have a single r. But I need an s squared, so I need another s here. And I also need a t, which means I need to add a t here. So then you double check yourself. 6 times 4 is 24. R squared s, r squared s. 6 times 6 is 36. R s squared t. R s squared t. So that's the final answer. But then, as a double check, you look back and say, well, is there anything common to this? Well, I have an r and st. The variables are good, but 4 and 6, something doesn't quite look right there. I can pull out something common to 4 and 6. The biggest thing I can divide into those things is the number 2, because 2 times 2 is 4, 2 times 3 is 6. So I'm like, oh man. But don't erase your problem. All you did was, when you did this problem, you didn't pull out the greatest common factor. You pulled out a factor that was present in both, but it wasn't the biggest one that you could have found. So it doesn't mean you start over. You can do it a bunch of different ways. So I guess to make it clearer, let's just say we're going to focus on this answer. If I gave you this problem, how would you factor it? Well, the biggest factor here is 2. So I'll just pull out a 2. What do I need to give me this? I need a 2r plus 2 times 3 is 6. st. Double check and agree with me that this multiplied together gives you this, 4r, 6st, right? So then to write your final answer, what you're really going to have here is you're going to have the 6rs from before, but then you're going to be multiplying that times what you got here, 2 times 2r plus 3st. So what you're going to have is 6 times 2 is 12, rs, 2r plus 3st. So 12rs, 2r plus 3st. That's the correct answer. That's the final answer. What did we learn from this? We learned that when we looked at the initial problem, the first thing we thought of as the greatest common factor of the numbers was actually 6. But it turns out, upon retrospection, that the greatest common factor here is not 6. The greatest common factor is actually 12. Because 12 times 2 is 24, you see it's here. 12 times 3 is 36, you see it's here. If you had thought, just maybe for a second longer, we might have realized that 12 was the greatest common factor, and we would have written it down and just eliminated all these intermediate steps. The reason I'm showing you this way is because very often you'll do this yourself. I mean, you just won't notice the biggest common factor. But if you get the answer, it doesn't mean you've done it wrong. It means you have more to do. Factor out something else, but then when you factor out and it comes into the front, you need to be multiplying it by what's already there to give you the final answer. At the end of the day, whatever you get at the very end should be multiplied together to give you what you started with. That is the concept of factoring. We're going to be spending the next probably 5 or 6 lessons on factoring of different types. It's because it's a really important topic. And it's mostly important because we're going to use factoring to solve lots of different kinds of equations later on. This factoring that we're doing is just the type of factoring where we're looking at each term, trying to find what's common to both terms, trying to find the greatest common factor of both terms, and then we pull that out and figure out what needs to go inside that parentheses to backwards multiply. And that's why I opened the lesson and told you that factoring is really distribution in reverse, or multiplication in reverse. Want to factor it out so that we can see what we need to multiply by to give us what we started. Saying that out loud gets very confusing. It's not so easy to understand, but seeing it in problem form, I think, is a lot easier. So solve all of these yourself. Get a pencil and paper. Make sure you can do everything from the simplest one all the way to the most complex one. Do them yourself. Follow me on to the next lesson and we'll get some more practice with factoring expressions in algebra.